Today we're going to start section 9.2, and you can see this is split into 3 days of notes. So for our first day, we're going to start talking about infinite series. And you might have heard me slip up a few times and talk about series instead of sequences in that first section, and that's because the rest of the chapter, we are pretty much going to be talking about series. So what is it? A series is just when you add up the terms of the sequence. So, for example, we use our summation symbol. So we might see something like, get rid of that. Might see something like the sum from, if the terms are denoted by a sub k, from k equals 1 to infinity. So adding up an infinite amount of terms, it would just be the first term plus the second term plus the third, all the way out to infinity. A sub 1, sub 2, sub 3 are the terms of the series, and A sub n is the nth term. And we had that notation with sequences. So you're just taking a sequence and adding up the terms. Now, there are some examples, this one's coming from our textbook, where we can look at a pattern where it's like 1/2 plus half of that, 1/4, plus half of that, 1/8, plus half of that, plus half of that. So the nth term, the pattern here is 1/2 to the n power, or 1/2 to the n. Those terms do add up to 1. We are going to come up with sort of a proof or how to show the math behind that, but for now, if this infinite series, I can add up an infinite number of terms to get an actual sum, that series is said to converge, just like we've been doing. With sequences, converge meant that the terms all approach a certain value. Here, the series has a finite sum. So the series, it's just like when we had infinite integrals and we had an area under an infinite curve. If that area converged, we're saying the same thing. The series has a finite sum. And then another thing that's kind of interesting, and again, we will get into the math behind this in a minute, but 1 plus 1/2 plus 1/3 plus 1/4, the pattern there is plus 1/n. That should say plus that. That does not add up to a finite sum. It adds up to infinity. It will continue to grow. So we say that that diverges. And again, in this chapter, that just means that the series has no finite sum. This will just keep growing. It'll keep growing and growing and growing. And it's kind of the same idea as the area that I said before that we talked about in chapter 8, where we said, well, some areas or some functions, decrease fast enough that their areas out toward infinity, the area under the curve is practically 0. So in the end, you end up adding 0 and you get some sort of finite area. Some functions or some series do not decrease fast enough, and so you can collect a few terms and keep getting another +1 and another +1. There's a really good example of this on YouTube that I'll try to find and link, because it's some math professor going through and showing, like, kind of proving to you or convincing you that, yeah, this is just going to keep adding up. I'm going to be able to get 1 plus another collection of terms to get me another +1, +1, etc. All right, so what about some other less obvious examples? I wouldn't say those two are obvious, but anyway, what about other examples? This entire chapter is dedicated to answering, does a series converge or diverge? And if a series converges, what is the actual sum? What does it converge to? So there are a series of what we call tests to perform to figure out whether or not a series converges or diverges. So before we get into all of that, we're going to start thinking about convergence just by looking at partial sums. Now, we had partial Riemann sums where we said, like, let's just use 4 rectangles to approximate the area underneath this curve. That was a partial sum. So here, partial sum is denoted by S sub n. That's the nth partial sum. It just means how many terms are you going to use to approximate the true sum of this infinite series. Okay, so S of 1 would be, I'm just going to use the first term. That's good enough. That's the sum of the series. Probably not a very good thing to practice. S sub 2, the second partial sum, would be the first term plus the second term. S sub 3, the third partial sum, would be the first three terms added together. And again, all of these would approximate the sum from k equals 1 to infinity of a sub k. They're exactly equal to the sum from 1 to n, but they're approximately equal to the sum from 1 to infinity. We're just using them to approximate. So let's put that on there. Approximation. A couple of notes down here. If the sequence of partial sums converges, so if the limit as n approaches infinity of the partial sum equals some sort of a number that exists, it's not infinity or negative infinity, then the series from 1 to infinity of a sub n converges. If I can show that a partial sum converges, I can say that the entire series converges to a sum. The limit S, the limit of the sequence of the partial sums, is referred to as the sum of the series. Now notice S right there doesn't have a little sub n that's a comma. So S is like not S sub n, this is a partial sum. This S without any little subscript there is like the sum that we're looking for. Think of it as like Riemann sum versus actual area. If the partial sum diverges, then the series, the infinite series, would also diverge. All right, so let's determine the convergence or divergence of the series. Let's go ahead and use here's what we want to do. Let me write out the steps first. We want to write a few, there's no set number, but write a few partial sums to find a pattern. The pattern that you're looking for is the nth partial sum. We're used to saying like it's the nth term. So you're coming up with that pattern. And then once you have that pattern, then step 3 is to take the limit as n approaches infinity of your pattern, of your partial sum, and see what happens. Does it come out to a number or does it come out to infinity? It comes out to a number, then the series converges. If it comes out to infinity, the series diverges. All right, so let's look at this. So if we start with our first partial sum. If we just use the first term, and this is already generated for us, so don't plug any numbers in here, but first term is just 1/2. So we could say, well, this series is going to add up to 1/2. Okay, we know that's not right. Second partial sum is 1/2 plus the next term is 1/4. So go ahead and add those up. So 2/4 plus 1/4, 3/4. I like to usually, I'm going to do like 4 terms and let's see what happens. 1/2 plus 1/4 plus 1/8. Well, we know 1/2 and 1/4 was 3/4, so I'm going to make that 6/8 plus 1/8, 7/8, and maybe I'll give myself one more. Okay, so again, for our notes, I'm writing all of this out, all of these sums, but hopefully in your homework you would just say, oh, the fourth partial sum is the third partial sum plus the next term, so 7/8 plus 1/16. 7/8 plus 1/16. So 14/16 plus 1/16, 15/16. All right, so here's what I'm looking at. Let's look at these terms that we have. Just separate them by commas. I'm not adding them together. I've generated a sequence. Sorry, the orange calculator is bothering me. Okay. Now this does continue on. I'm trying to come up with a pattern. So this was when n equals 1. This was when n equals 2, n equals 3, n equals 4. Remember in section 1 we did this a little bit. We had to come up with the nth term or try to find the pattern. So it's coming into handy here. So what is the nth term going to be? Let's see. My s sub n, I think I can figure out the denominator. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the n. And then the numerator, let's see, 1, 3, 7, 15. So all of these are 1 less than the denominator. So I think 2 to the n minus 1 is going to fit, right? So I think that's our nth partial sum. So we wrote a few terms. We figured out the pattern for those terms, for the partial sums. And so back to this idea here, the limit of the partial sum, if that becomes a number, then the series is going to converge because when I say partial sum here, I'm talking about the pattern for the terms, the nth term. So it's not like you're not using something inaccurate. You're not using like the 15/16 and saying, oh, that's what it adds up to. No, we're saying, okay, if we get to the limit as n approaches infinity of 2 to the n minus 1 over 2 to the n. Now, this isn't quite a tie. I should technically do L'Hopital's on this. So I should technically, this is 1. But I should technically say, well, the limit as n approaches infinity of 2 to the n minus 1 equals infinity. And that also equals the limit as n approaches infinity of 2 to the n. Okay, so then I should say, I use L'Hopital's. The reason I'm sort of half doing this is because most of these problems, and actually our chapter 9 test, or one of them, the first test we have, is going to be all multiple choice. So most of these problems fall into multiple choice, and multiple choice doesn't care whether you've properly done L'Hopital's or not. It's more about, can you do it in your head? So anyway, this minus 1 becomes pretty minuscule as you head toward infinity. So this is practically 1. Anyway, you can see here that it divides out to 1. And so you do get 1. All right. So the idea here is that I got a number, right? So what's my conclusion? Therefore, the sum from 1 to infinity, terms 1, an infinite number of terms from the first out to infinity, of 1 over 2 to the n, converges. Right? And let's see. I don't want to say what this adds up to yet. I don't want to say that it converges to 1. I do think that that's true, but I don't want to get ahead of myself on the geometric series. So I'm just, for now, we're just answering converges or diverges. It doesn't say if it converges, find the value. All right, so part B, the sum from 1 to infinity of 1. So remember, the 1 to infinity part means you're adding an infinite number of terms, starting with the first one. Now, you can see without doing any sort of work, this diverges, right? Is there any reason this would stop adding up at some point? No, it's always going to be 1 plus 1 plus 1. It's going to equal infinity. So, I mean, if you wanted to show work for it, you could say, hey, the limit as n approaches infinity of, there's no s sub n to come up with, it's just 1. So it would be the limit as n approaches infinity of 1 plus 1 plus 1, or no, I'm sorry, there would be an s of n to come up with, but I don't want to, but it would be, the first one is 1, second one is 2, so this would just be n, right? Third one would be 3. Okay, so anyway, the limit as n approaches infinity of n is infinity. I put thought into that though. It converges. All right, so example 1a is an example of a geometric series. So we're going to talk about how to do this a faster way. This is why I didn't want to answer this yet. So I don't want to always have to do L'Hopital's. Okay. First of all, what is a geometric series? What does it look like? So in a geometric series, each term is found by multiplying the preceding term by the same number, and that number would be r. So they're set up like this. You might have some sort of a constant, and you have r, which is some sort of a fraction. It's a ratio, and it's raised to the n power. Okay, so the first term would be, if we're starting at 0, notice, would be a times r to the 0, or just a. And then plus a times r plus a times r squared. Now, if you divide these consecutive terms, they would divide out to r. R is the ratio. In a geometric series, if r is between 0 and 1, and I say absolute value because r could be negative, it could be an alternating series, but as long as that's a fraction between 0 and 1, then the series converges, and we know what it converges to. It has a nice little formula. It converges to a over 1 minus r. And a is the first term. Now that's important because a could be the first term when you plug in 0, or it could be that the series starts at 1 or 2 or whatever. So whatever series you're starting at, you plug in that n in for r, and whatever the first term of that series would be is what goes in your numerator. If the geometric series has an r that's greater than or equal to 1, so like there was a 1 that diverged, or if I just had like 2 to the n, that's going to keep growing, so the series diverges. All right, so let's practice our geometric test. Determine the convergence or divergence of series. Again, it'll be geometric as long as you have just a single term to the n power. So if I look at this first one, I have r, which is equal to 3 over 2, and that's greater than or equal to 1. I'm just going to make a note here. There's technically a 1 in front of here, so there is an a of 1. It's just good to identify those parts, I think. I'm sorry, a of 0, that like plugging in 0, that first term would be 1. 3 over 2 to the 0 is just 1. Anyway, since r is greater than or equal to 1, let's say it like this. I'm trying to answer how I want you to do it on the AP test. Diverges by geometric series test. The AP test, this will be multiple choice, and they will give you, like, you have to choose the best test. So this diverges by geometric series test is what it'll say, or it'll say diverges by some other test that we learned. There are, I think, 10 of these tests, and that would be wrong if you're using a different test that doesn't apply. All right, let's look at B. Now, the only thing being raised to the n is the 2. The 3 is really just a constant. And if you want to rewrite this, it might be smart to write it as 3 times, since the 2's in the denominator, I'm going to say 1/2 to the n. That puts it more in the form that we're used to. So r is 1/2, which is less than 1. So this is going to converge. It's the r that tells you converge or diverge. Let's add that to our example there. And then if I know that the series converges, that's when I should really bother finding a. So the first term will be a when I plug in 0. So what does that come out to? That comes out to 3 times 1/2 to the 0, or 3 times 1. So remember, if a geometric series converges, it converges to a, the first term, over 1 minus r. So for us, this is going to converge to 3 over 1 minus 1/2. 3 over 1/2 is equal to 6. This series, this infinite series, adds up to 6. So it must decrease fast enough that as you get out to terms way out toward infinity, you're practically adding 0. And so it ends up that you get a sum of 6. All right, what about the next one? This one looks a little weird because you've got 2 to the n plus 1. So remember, 2 to the n plus 1 is the same as 2 to the first times 2 to the n. That's a really important rule to know. We're going to need to split things up a lot like that. So if I look at it this way, this is just 2 to the first times 2 to the n over 9 to the n. And I want to get this more in a geometric series form. So I'm going to rewrite it one more time. The 2 stays out in front. And then instead of 2 to the n over 9 to the n, make it 2/9 to the n power. So here you can see that r is 2/9, which is less than 1. So I know that this is a series that converges. Oh, sorry, in part B, we should always say converges by geometric series test. We're not going to abbreviate these like GST or whatever because we have too many tests and it'd be too many abbreviations. So we just need to write them out. All right, so this converges by geometric series test, and I can also say what it converges to. Depending on the test, we won't always be able to say what it converges to, but this one we can. What does it converge to? Well, what is the first term? Plug in 0, it says, for n. So 2 times 2/9 to 0 is 2. Now, I'm taking the time to plug that in because sometimes it tells you, like I said, to start at the first when n equals 1, and that would be 4/9 then is my first term. So I have to pay attention. This is 2 over 7/9, which is 18 over 7. That's what it converges to. All right, what about D? This is already in its geometric form, so that's good. Our R is E over pi. Is that less than 1? Let's see. E is 2 point something. Pi is 3 point something. So yeah, that's less than 1. Our A sub 0 term would be 2 times E over pi to the 0, so 2. So I know that this series converges. Converges by the geometric series test. And what does it converge to? A over 1 minus R. Now you might see if you're searching for your answer, they might simplify that complex fraction. So remember, we can get rid of the complex fraction by multiplying by pi over pi. And so now it's 2 pi over pi minus e. That's what it converges to. All right, so what are some properties of a convergent series? So like what if we're combining more than one? So let's let the sum of a sub n and the sum of b sub n be convergent series, and let a, b, and c be real numbers. Okay, so let's say the first infinite series has a sum of a, second infinite series has a sum of b. Then the following series would have to also converge, and it would be to the indicated sum. So if I had a constant c multiplied by a sub n, then the sum of that series would be c times a, because the infinite series of a sub n adds up to a, and we're just scaling that up. All right, my next one, if I add two infinite series together, or two convergent series together, excuse me, then I can just add their sums. It would be a plus b. And I can also subtract them, a minus b. All right. I want to do a couple more. Let me just throw in one more example, just one, of, let's see. Oh, no, I lied. I want to do two examples. I want to do one where r is negative, just to make sure we've seen that. You'll come across this in the homework, I'm sure. And then the other one I want to do is when we start at something other than 0. So let's say we start at like 3. And I don't know. Okay. So our first series is the sum from 0 to infinity of negative 1/2 to the n. So we know that r is negative 1/2. Back here when I said the absolute value of r is between 0 and 1, that's just to tell you that, like, hey, you have a fraction of 1/2, so it converges. So you're not meant to make r positive. I just wanted to point that out. The a sub 0 term would be 1. So this is going to add up to 1 over 1 minus negative 1/2. It's going to add up to 1 over 1 plus 1/2, or 3 over 2, which is 2/3. Okay, so r can be negative, and you would plug it in as negative into your formula. For this one, r is 1/3. It's not a sub 0, it's a sub 3. Start adding these up at the third term. All right, well, so that's equal to 2 times 1/3 to the 3. All right, so that's 2 over 27, right? So then when I do my series, it's the first term, 2 over 27, over 1 minus r. If I multiply that by 27 over 27, that gives me 2 over 27 minus 9. 2 over 18, which is 1 over 9. All right, so you do need to pay attention to what that first number is. Often it's 0, but sometimes it's not. So you do have to pay attention. All right, that's it for today.